A single AI-enabled search query can use 25 to 30 times more power than traditional web search. So AI is not just powerful, it is power hungry. And that brings us to the question for today. It's not just about building more compute capacity, it's about ensuring that access to compute is broad-based, affordable, geographically distributed, and aligned with national priorities. And this is very much how India and the India AI mission is seeking to tackle this question. But today, much of India's data center capacity is concentrated in major metros. But if AI is to deliver impact nationwide, infrastructure needs to be moved closer to users. Regional capacity can reduce latency, saving those milliseconds that create a better user experience, support real-time and edge use cases, and unlock innovation beyond traditional hubs. Of course, none of this is simple, from advanced chip access to environmental and resource factors, having the right workforce skills, and regulatory considerations. These are ecosystem challenges. And that's precisely why we have this panel, leaders across AI infrastructure, technology, and governance to help us explore how the next phase of compute expansion can be more distributed, resilient, and inclusive. With that, let me introduce our panelists. Anne Robinson is Senior Vice President and Chief Legal Officer at IBM, where she leads the company's global legal and governance functions. She oversees legal strategy, regulatory engagement, compliance, and board governance. Durga Maladi is Executive Vice President and General Manager at Qualcomm, where he leads technology and IP planning across the company's businesses spanning edge services, edge devices, and data center solutions. His responsibilities include processors, connectivity, AI platforms, infrastructure, and network management, supporting Qualcomm's innovation across compute, communications, and intelligent systems. Ipsita Dasgupta is a Senior Vice President and Managing Director of HP India, Bangladesh, and Sri Lanka, where she leads HP's business across commercial, consumer, and public sector markets. She is responsible for go-to-market strategy and P&L for one of HP's fastest growing regions. Shrikant Cherukuri is Senior Manager, Envis Solutions Architecture at NVIDIA, where he leads solution architecture initiatives focused on deploying in NVIDIA DGX, HGX, and data center scale infrastructure solutions for enterprise customers. Based in Santa Clara, he supports the design and implementation of high-performance computing and AI infrastructure across global deployments. Dr. Neeraj Kumar is Chief Data Scientist in the Advanced Computing, Mathematics, and Data Division at Pacific Northwest National Laboratory. He leads data science, artificial intelligence, and applied mathematics initiatives, supporting the laboratory's national security and engineering missions. His work focuses on advancing scalable AL/ML capabilities, natural language processing, quantum computing, and innovative modeling and simulation methods across multidisciplinary domains. As Ericsson's CTO for Asia Pacific, Marcus Everbring is responsible for driving technology alignment as well as long-term technology strategies for Ericsson in the Asia Pacific. Magnus has been with Ericsson for more than 30 years and has held several senior executive positions within Ericsson research, development, business units, as well as in customer accounts. All right, so we can dive right in. And we can maybe start with Neeraj. Neeraj, I think national laboratories in the US have long treated compute as scientific infrastructure. What lessons can emerging economies and middle powers like India learn from the US, and how should they be thinking about some of these issues?
Thank you, Roy. Thank you, everybody. Thank you, my co-panelists and the audience. So I want to start answering this question by saying that The U.S. Department of Energy has 17 national laboratories, and each of these national laboratory has their kind of a mission. It's like mission based. So to give you an idea and kind of build a foundation, that one of the fastest computer that has been built by U.S. Department of Energy's National Laboratory, Oak Ridge National Laboratory, with the 1.1 sort of a flops efficiency, and that supercomputer, or we can say the data center, wasn't built by a single organization. It was a partnership. With Department of Energy, U.S. Department of Energy. It was partnership with AMD, partnership with HP, and many other organizations. So the partnership is the key in order to build really the next generational sort of a energy efficient data centers. What we have learned over the time, kind of a three different things, that I would like to share here. Number one, it's kind of a co-investment. It's a private-public partnership, government-public partnership. So all these data centers that we have built, it's in the interest of like really building scientific infrastructure, scientific kind of a legacy compute that can not only generate sort of a discovery engine, but also solve challenging mission-driven problems. So compute is not really as kind of a architecture, or it's kind of a platform where we can run a bunch of different things. What compute can be considered as integrated way, where the data centers, where the energy efficiency and where the power can be integrated in such a manner that we can drive both scientific discovery, energy systems, as well as some security, national security sort of applications. So it's a blend of different things. And within Department of Energy, the investment on the compute side has been really humongous to push the boundaries on the energy efficient computing. So the second, I would say, is the distribution. So all these, data centers that we have, supercomputers that we have, it's distributed among U.S., among different states, in national laboratory. So that's a key combination of, like, we really don't want to localize or centralize our data center in a one location in a metropolitan city, but rather moving forward in a maybe tier 2, tier 3 sort of cities, where those data center can be integrated in such a way that the revenue, sort of the infrastructure can be utilized across nation or globally. The third thing that I would like to share is, like, invest not only in compute, but also brute force brute force and workforce development. Why I say this? Because this is a critical pillar. The compute, the infrastructure that we have been building, it's going to go old, but the investment that we are doing in people, it's going to go way far. So to summarize, answer, it's a combination of many things: co-investment, public-private partnership, and really regional distribution of data centers, where the power, where the energy, where the chip manufacturing can be kind of a co-design at the same place. But not only that, also investment on the workforce development. Thank you.
Thank you, Neeraj. Coming to you, Anne, can you tell us a little bit about how sovereign cloud models shape the digital backbone of a country, and how do you at IBM sort of reconcile, sovereign cloud along with, looking at ensuring that fragmentation doesn't happen within the ecosystem?
So first of all, I'd also like to thank the sponsors for giving IBM an opportunity to participate in these really important conversations. And then the second thing I would observe, which is something that we've talked a lot about throughout the conference, is this question of balance. And so when I think about sovereignty, I think that too is subject to a question of balance. Right? If I'm thinking about India and other countries, sovereign nations want to make sure that they have control. So they'd like assurances that their data and critical infrastructure are subject to local laws, oversight and the things that give them the autonomy and the ability to operate without interference. But then they're also trying to drive innovation and growth. And so, how do you strike the right balance, between those two things? So, from IBM's perspective, the way we think about it is sovereign by design, and that aligns our clients' interests and their infrastructure with the requirements of the local jurisdictions that they do business with. So that's making sure that data is resident in those countries and built into the architecture. It's that customers, so that the customer manages encryption keys so that they have the control. It's also about making sure that the systems are transparent and who can access the data, where you can access the data, under what circumstances you can access the data, are all embedded into the system, and that there's auditability associated with those features. This is also a reason why hybrid cloud is so important, because it allows a broad spectrum of ecosystems to participate, right? So you have public systems, you have private systems, then you have on-prem. And for highly regulated industries, that balance is also really important to complying with sovereign expectations while managing businesses for growth. So having local hosting, local operations, and local compliance all align really nicely. But those platforms that anyone is leveraging have to be interoperable. And that interoperability is the very thing that I think prevents fragmentation.
Thank you so much, Anne. Durga, if I can come to you, how do we design and deploy models that intelligently split AI workloads between the cloud, where we have massive computing power, and the edge, where speed, low latency, and privacy really matter?
There we go. That works. First of all, thanks for hosting me over here and along with the rest of the panelists. And I was thinking about, you mentioned earlier that the title is a bit of a mouthful, and I kind of latched on to three words over there: democratization, compute, and what does regional mean in the age of AI? I think one of the observations that comes in very quickly, especially for someone like Qualcomm, we have a unique vantage point in terms of powering the compute, the SoCs that go into everything ranging from doorbells to smartphones and PCs and AR glasses, and increasingly into automotive and now into data center. So we do have a perspective of what exactly compute means when we take it across all these different very diverse segments. And the first thing is to make sure that we understand that today's AI models are far more powerful than what they used to be even 3 years back. Just case in point, if you were to take a look at GPT-3 back on November 30th of 2022, when we all woke up to what was called as a ChatGPT moment, that model was 175 billion parameter models. And if I were to take any of the models that actually exist today, which are like in the 1/10th or 1/20th the parameters, whether it is, Anna sitting next to me, so I can talk a little bit about the models coming in from IBM, but there's so many other models from China, from US, and most recently from Servam. They're really tiny and they're really suited for deploying in all the devices that all of us carry around with us, which means we have a foundational layer of having the ability to run very sophisticated models. They're not very large, but very sophisticated models directly on devices. That is step one. It's a means towards an end goal, but it's not the end goal in itself. The second part is that it? First of all, why do you want to actually run these models on the device? Why can't you just run everything in the cloud, just have a good connectivity to it? And the answer to it is, well, the first level answer is because we can. We can run these models on devices, so sure, why not? Connectivity ranges depending upon where you are, and you might not always have the best connectivity, so you can do that. But there's a second point, and that is a distributed computing horsepower that goes all the way from devices into the data center. And I would argue that there are three nodes associated with it: devices, somewhere at the edge cloud, as was described earlier, servers that are located right in the enterprises so that you can maintain a lot of the data right there and perform localized inferencing, and of course the data centers where there's much larger workloads that can be run along with training. And that brings me to the second part. The compute aspect of AI is largely about AI inference these days. Training is about making the models. That's step one. But the usage of AI for all sorts of different use cases really hinges upon inference. And so we really see an ability to do inference in devices at the edge and all the way into the data center, which leads us to a hybrid AI concept where you have a mix and match of the workloads. Depending upon what is the workload, you might want to run it on device, or you might want to run it at the edge, or all the way into the cloud. Conversely, you might have, and a lot of us nowadays use models which have what is called as a real-time routing. You can get a very quick answer, or you can get a far more thoughtful answer, which is called a chain of thought reasoning. And you could actually argue that those sorts of models can run, the chain of thought reasoning can be done a little more at the edge and in the data center, and the faster responses can come from the devices itself. As Qualcomm, we are powering all the devices across the tiers to make sure that we are in a position to run these models. We are not a model creator. We ingest them and make sure that they run extremely efficiently. And that basically is the starting point for the rest of the conversation. Final argument on regional models. It's very important to understand that models are literally nowadays in every part of the world. And it is extremely important to fully embrace and adopt and ingest sovereign models that come in. There are national champions and there are all kinds of other models, because at the end of the day, these models are being used for a natural interface to devices around us. And I would argue that usage of keyboards and touchscreen is only one way of doing it, but voice is the most natural user interface to devices around us. So any glasses that you pick up over there, I would like to speak in some local language to be able to get away with it, which means you must have all the languages adopted. So as Qualcomm, we are doing all of the above to make sure that, as you put it, democratize the compute in the regional infrastructure.
Thank you so much, Durga. If I can come to Ipsita, I mean, Durga has already sort of talked about edge AI and distributed processing to some degree. How does that sort of reshape digital sovereignty, particularly for a country like India, where having the scale of hyperscale data center investments may not be possible on the scale of what has happened in the US, for example?
And you're right, Roy. Both you, who started off talking a little bit about the requirement for balance, and all the speakers since you have talked about a number of things that I would have said. So I'm actually going to create a visualization of some of these concepts and why this hybrid of LLM and SLM is going to be really important, and how we can't just depend on the hyperscale model. But before I do that, again, I want to say that thank you for having me, but also it's so exciting to see the world descend in Delhi today and over the last few days and through this week. And it's especially nice sitting next to someone from IBM, because I started my career there, so I feel like I've come full circle now. So let me just create a bit of an image to start off with. The Honorable Finance Minister, when she released the budget on February 1st, talked about India's areas of focus. And while she talked about data centers and AI and technology, on the other side, she talked about 30 million workers in the coconut industry. And she talked about bringing AI to farmers. And that is what describes India. India has a unique way of taking technology and adopting it to what it needs to be for India, and probably better than anywhere else in the world, as the digital payment stack has shown us. If you add up digital payments of the US and China combined in any given day, they don't add up to the digital payments made in India in the same day. I have no doubt that AI will have the same effect on India and through India. So I love this concept of balance and hybrid, and so let me approach that in the context of what I've just said. And let me just give you a view. 1 gigawatt of compute, 1 gigawatt of AI data center capacity will cost about $50 to $60 billion. Just to give you a sense of what 1 gigawatt means, it's enough to power 700,000 to 1 million homes, essentially a small Indian city. This is enormous, and you said it at the beginning. But many of the things that we are going to be using AI for don't require this level of capacity and capability, right? So what are those things? Again, let me bring some visualization to this. These are things like AI services to farmers, citizen services, vernacular services, workflow models for MSMEs, education and learning capacity and capabilities for 200 million students in India. So truly, I think we should both embrace the ambition of hyperscaling with the pragmatism of SLMs on the edge.
No, that's a great suggestion, Ipsita. So I can probably move on to Magnus at this point to maybe talk about the network aspects of this. Particularly the concept of having 5G and compute really going hand in hand, right? And from an India perspective, how do you see India's positioning on 5G and eventually a 6G rollout? And what are some of the infrastructure gaps, but that must be solved in real time to sort of enable real time AI at the edge?
Okay, thank you. Well, first of all, democratizing then through regional infrastructure. I think a key thing for allowing people in society to use AI-based applications and leverage on the cloud compute is to connect the two. And that, I argue, we do with mobile networks. And that's not the least visible here in India. Over 800 million mobile internet users and the number of fixed homes that have an internet connection, less than 50 million. It's absolutely the way that internet is being accessed. Then with 5G, it becomes even stronger in India. India has today some of the absolutely best 5G networks. Over 500,000 radio base stations are deployed. Well over 90% of all Indians are in 5G coverage area, considerably better than most nations. And that is, of course, an extremely good platform to drive how AI is being adopted in society. Add to that the digital stack. UPI is a simple example of how digitalization comes when you have the internet in the palm of your hand. As we do that going forward then, we have gigantic networks deployed. They connect today to central data centers where certainly AI compute can be made and will be made and should be made to a very large degree. There is, of course, also other applications that may gain from being closer to the user. Could even be in the device, like Qualcomm would have a craving for naturally. And it will be there, some of it. Some of it will be closer, but on the infrastructure side. Some of it will be in distributed, regional, and central centra. Already today, we support this, and it's a matter of gradually building it out depending on what the needs are. As we progress then towards 6G, this will be even more enhanced. 6G, we say, is AI native from the start. We advocate to have a very smooth evolution up there so that we can leverage it quickly, have a wide, broad footprint from the very onset of 6G in a few years to go. And again, I think India is so well positioned to leverage its current position, driving the innovation now on top of the networks with AI-based applications, and then leading the way to 6G in a few years to come.
Thanks so much, Magnus. If I can just switch gears a bit, we at the beginning we did talk about some of the challenges that are posed by building out this kind of infrastructure, right? And we've already heard a number of good suggestions on what kind of models are actually going to work well in India, right? And if I can ask Shrikant to talk about, actually when we come to the chips and talking about energy efficiency in terms of the chips, could you talk about what sort of work is being done in that area, and where does this sort of fit into the sort of India story in terms of how the build out, what the build out is going to look like?
Yeah. First of all, very happy to be here and talking to you all. If you look back 2 years before the ChatGPT moment blew the doors open on the AI factory build out that we're looking at today. If you look pre that moment, I would say there's a couple of things that are worth highlighting. One, I never got stopped on the street when I wore an NVIDIA T-shirt. Today, I get stopped routinely on airports everywhere because the fundamental idea of a chip has changed from a CPU to a GPU. And in the last 2 years, I would say, or in the what I would call the first generation of AI build out was relying on traditional data centers. Now, how were traditional data centers, how was that infrastructure designed? It was designed with very high resiliency, very high redundancy, because it was more on whether it's on-prem on cloud. There was a lot of very mission critical applications running on it. But that ended up wasting a lot of power. Like you have almost 15 to 50% of power being utilized not in compute and not on the application workloads, but due to resiliency and redundancy, as well as the full stack not being co-designed. So in the next generation of build out and the next generation of chips and systems that NVIDIA is architecting, including networking, the way we think about this is what we call extreme co-design. I think Neeraj mentioned the word co-design. We've taken that to extreme co-design. Now, what does that mean? Everywhere from chip to the rack scale systems, to the networking that's connecting those rack scale systems, to the data center that's housing all of those, up to a gigawatt scale, we co-design all of that in alignment with each other, so that you're using the 15 to 50% power that I mentioned earlier is not going towards auxiliary usage, but it's going towards compute. So you're getting as many tokens as possible out of every single watt. Now, why is that important? In the U.S., primarily in the U.S., it's very power constrained right now. Everybody's grabbing whatever capacity they can get. The data centers are not optimized for it. But in the global South, like countries like India, where they're making plants and investing in infrastructure, this is a golden opportunity to really cost optimize what that AI tokens are going to look like. So this is an opportunity for all these countries to grab. And second, what is the second principle in co-designing? When we think about data center infrastructure, it's a long lead time item, right? Like you're talking about when you build a data center, you're talking about its life cycle being about 10 to 15 years. So you don't want to change that infrastructure and spend a lot of money retrofitting your data centers every generation. So the way we are looking at it is the most future-proof design, the most optimized design that incorporates liquid cooling, high-density racks, and with each generation of chips, that same technology should be able to accommodate within the same data center. So and what's the third principle of how we're looking at this is, again, going back to traditional data centers, you had a large manual operational staff. You took very little advantage of all the data sets at different layers of data centers being integrated. So how do we redo that in the age of AI? We connect every telemetry from the chip right up until the facility level, right up until the grid level, and optimize so that it's, again, with the use of AI for AI factories, you could optimize how each watt is used and at the right place, right? So for example, when your workloads are not that high, you could drive down and throttle the power. And when you have your software helping with redundancy and changing workloads as you lose some racks, you have the opportunity to not have 2n redundancy, for example. So you could use as much power as possible for a generation of tokens. So if I, this blueprint for building a gigawatt scale optimized AI factory, we call it DSX. So I heavily encourage the audience to go look at our blogs on DSX and the blueprint to build a data center like that.
No, thanks, Shrikant. Durga, if I can turn to you again, coming back to this point about challenges, right? As in, I don't think it can be underestimated, and we really want to emphasize the kinds of demands, energy, and otherwise when we shift from traditional workloads to AI workloads, right? So how particularly from an environmental perspective and a resource perspective, Durga, could you maybe take us through some of these challenges and anything else that you are seeing as well?
Maybe I'll just in terms of the overall challenges, maybe I'll say a few words about, like, in general, when you try to break down the AI problem statement, how does it pan out? We've talked a lot about compute and we've talked about the data center buildouts and so on. So let me throw some numbers over here. If you were to take a typical data center rack, and we are in the business now, we are newbies in that, we know that, but a typical rack is about 150 kilowatts. And the rollout that we expect in data centers is about 300 gigawatts coming up. So you do the math and you say, okay, fine, that's about 2 million racks that are needed. Each rack consumes 150, or we talked about the amount of power that's needed, but there's something else that's needed inside the rack, and that's the amount of memory that goes in. Typical rack is about 40 terabytes. It's about 43 terabytes to be very specific, and you multiply that, that's about 80 exabytes of memory that's needed. And most of the industry, like those of us who are in the trenches, when we deal with this, we know that today's memory, there's a massive memory shortage in the industry today. And that's a second variable that's coming in. It's not so much about compute, but there's memory as well. Uh, Smartphones, there's about 1.2 billion smartphones that are sold in the world today. Each of them average of about 8 to 10 gigabytes of memory. That means an industry which was really focused on smartphones was capacity dimensioned for about 10 exabytes. And instead now you have to go from 10 to like adding another 80 on top. That's a challenge, by the way, as an industry we are facing, and it'll take a little bit of time to solve it. Hopefully not a whole lot. But now when you take it back from there and then you ask yourselves the question, as we build out these data centers and we try to rely as much as possible on hybrid AI, what is the best architecture that goes into these data centers to minimize the power consumption and minimize or maximize the energy efficiency? And historically, the argument was, well, you want as much compute as possible, and that's what actually takes up a lot of the power. And actually, as rightfully pointed out by my colleague here from NVIDIA, there are ways of making sure that you don't constantly use the power, which is actually a pretty good step because it's absolutely critical. But another way of looking at it is what is the best way to make sure that we harness the inference capabilities, which might not be the same thing as training, depending upon how you do. Historically, we used to design for training and use the same solutions for inference. These days, increasingly, we are actually using, when you take a look at the prefill stage, that's compute dominated, but the decode stage happens to be memory bandwidth dominated. It doesn't matter how much of compute you throw at it, actually doesn't make a difference. So we got to be smart about thinking what is the best way to roll it out, even in the data centers, and have a technology trend that actually shifts a little bit more compute plus memory, thinking about both of it, because we think that that starts minimizing the energy efficiency. And the second, or maximizing the energy efficiency. The second part is the hybrid AI is not just a slogan. It is something that you have to embrace because we all have the spare capacity and horsepower that is left idling in all of our smartphones, all of our compute devices, in all the on-prem servers, on everywhere else. We have to find ways of utilizing that as well. Otherwise, we're not actually looking at the problem. We are trying to first throw a solution and creating a problem around it. Rather, we have to think more holistically to bring down the network plus device power consumption. And we believe that's the right way to go about it.
No. Thanks so much, Durga. So, Anne, if I can turn to you on this question of sustainability, right? Obviously, there's one way of thinking about it as, look, this is a regulatory consideration, it's a compliance consideration, but it's now also really becoming a competitive differentiator as well, right? So how should we be, should data center operators be thinking about sustainability that is, in a way, much more holistic and sort of goes beyond just compliance?
Well, thank you for the easiest question of the panel because, frankly, you've heard the answer, right? So we've heard a lot about how important it is not to just think about sustainability as a reporting obligation or a regulatory issue, but that it has to be embedded in a very foundational way into how data centers are operated. Some of the things we've talked about are just using AI and using technology to be very thoughtful about how you manage energy consumption, how you manage water usage. So using and leveraging technology to think about sustainability also is a very practical way of thinking about the way you operate your business. We've talked a lot, I think we've heard three panelists talk about architectural choices. So leveraging hybrid cloud, thinking about workload optimization, where you're being very intentional and thoughtful about putting the work where it's most energy efficient, where it's most business sensible, rather than just thinking about it where capacity exists. And then increasingly leveraging the data that you derive from some of those two choices I just talked about, so that you have the insights and you have an auditable trail of data that you can then help you to inform choices moving forward. So those are some of the things I think that are key. IBM has been working on solutions to drive energy conservation and make sure that data center cooling efficiency and capacity is well managed. But in addition to that, I think that one other thing that I would mention is that, particularly in a growing environment where we talk a lot about the need to build new data centers, and we do need to build new hardware and infrastructure in a very thoughtful geographic way. The reality is modernization and automation within existing data centers is also a way to get there faster, frankly. So you can deliver faster sustainability results as well as business outcomes if we leverage existing data centers in a more thoughtful and intentional way.
Thanks. And Ipsita, if I can come to you again, I think Durga has talked about this concept of using unused capacity, idle capacity. How do you sort of think about that particular issue? And I think we already talked about the on-device, edge device. How does this all sort of tie together?
Yeah. Again, great question, and the answer is in the question itself. We need to use this capacity. The amount of ghost compute that we're sitting on is just a gold mine, and by ghost compute we mean this compute capacity that's sitting idle. And just to give some examples of where it's sitting idle, enterprises servers that are running at less than 30% utilization, PCs, laptops, and workstations with powerful CPUs and NPUs sitting idle for most of the day, edge nodes in factories, schools, and offices, and local microservers deployed across telcos and ISPs. This is not just an engineering problem to solve, but it's a sustainability imperative. And what does it do? It actually helps us relieve some of the pressure on centralized data centers, but also allows a number of things to happen that are important and unique to markets like India and other growth markets, reduce the number of data center queries and therefore lower power consumption, keeps sensitive data local, allows us to get to low connectivity regions. So all in all, we absolutely have to mine this ghost compute capability and capacity that we have across the country.
Thanks, Ipsita. So, Neeraj, I did want to come to you quickly. I know we want to take some questions from the audience. So, Neeraj, I know you have a sort of different perspective on how we can sort of build this from the ground up, where energy is really, instead of thinking about data centers and how we tack on the energy issues and deal with them thereafter, how do we think about this from the ground up?
So this is the question that goes right to the heart of what keeps me up at night. And here's the uncomfortable truth. Globally, we are building AI data centers and then scrambling to think about where the power is going to come from. This is exactly like building a Formula F1 cars and then thinking about where the fuels is going to come from, and it's backwards, right? So as a leading organization, this is exactly what we have been thinking about at the national scale. How do you design energy system and compute system as one integrated platform or architecture, And I want to give you a flavor of that. U.S. Department of Energy recently released a Genesis mission, a mission to really integrate the power of AI the use of energy efficient system and the scalability of compute to solve grand challenges problem. The problem that not a single organization or a single country can really solve, like very, very huge problems. And at the heart of that is how do we really learn from what we have done so far, what we have really done on the foundation model side, and how they can push the boundaries on the science, technology, engineering in a way that we would be much more efficient when building sort of a ground up data centers. So the idea here is learning from AI, or at least learning from really much embedded reasoning systems. How to kind of build some scalable, portable, or regional data centers. And from an infrastructure sort of a point of view, I think about these as a three layers. Layer one is really at the forefront of sustainable energy sources. How do we really use it? Like India AI has already been really progressing in that direction using 180 plus sort of megawatt centers. But not only that, the layer two is more like where the power is going to come from. How do we efficiently get the power in a short term? And that's where the nuclear reactor sort of a AI related power that can be generated at the place where the data centers are to run a megawatts of data centers. And then the third layer is more grid optimization. How do we use AI on the grid management, grid optimization? So if we combine these three layers, this is what I think about pragmatically, and this is a opportunity for any single nation to think about integrated platform, not only data center but also the compute, also the power. So as most of you have phones, you are creating data, right? We are going to run out of power at some point because the data is exponentially increasing. Either we need to come up with energy efficient computer, as my panelists talk about, or we need to think about other sources of power that can really keep these data centers going. So India has opportunity to really build ground up foundation in that direction and learn from West, to not juggle with the one or the other, but maybe combination.
Thanks, Neeraj. Okay, I'll just quickly come to Magnus on this point of how do mobile networks how they contribute to perhaps reducing carbon footprint from an AI perspective? I know you had some thoughts on this, Magnus.
Okay, thank you. So there are two aspects of this one. One is the networks themselves. There, of course, we work very hard with it. The hardware base is reducing the power need by 25 to 30% with every new issue of products. That is about once every 18 months. On top of that is, of course, what we do in the software. And here, AI-based algorithms comes in to reduce power further. So the networks are becoming more efficient, and while they're becoming more efficient, they certainly take a heavier load. So the energy per bit goes down in that sense. Even more important is, of course, how they support the rest of society. And they're being connected and you being data-driven saves energy even furthermore. I think we've seen now in many industrial examples how industries, by being connected, can derive a higher value. In mining, we've seen examples of drastically reducing the need for ventilation by being data-driven and by knowing what the actual air quality is. So the networks themselves drive higher energy efficiency and the use of them even more so. Thank you very much.
Thanks, Magnus. If I can open it up to questions, please.
Excellent panel, and I like the fact that sustainability was the core of discussion and designing the sustainability in through multiple different ways. central. There's a one piece of sustainability that I haven't heard in the conference yet,
Yes.
which is the electronic waste. We have about 2 million tons of electronic waste in India, forget worldwide, and 60 to 70% is not recycled. So that's a challenge, not addressed, just sitting there, ignored, piling up.
No,
And
thanks so much. Is that a question which anyone or a topic which anyone wants to take up? Electronic waste and how we're dealing with it? Sure. Go ahead.
Thank you very much. I think a wonderful session. I must congratulate. I'm Dr. Pawan Saharan from Stanford. I run a Biomix Network Limited there, an inventor of artificial intelligence-based knowledge acquisition tools that IBM has requested me to license. We'll talk later. But my question here is, because I want to tell her, so that people keep talking about data centers in space, and especially Elon and other stuff people keep talking about, So what is a realistic, I'll start with Neeraj. I think he has some ground idea. I don't think the idea you gave about, generating power from nuclear is feasible at this time, maybe in 10 years from now. But how does the space, because India is a very profound space and also NASA,
No.
how does it work? Is it feasible? And then talk to Ms. Das Gupta and Annie. Thank you.
No, thanks. We can take a couple more questions.
So this entire capex flywheel that's been created, do you think it's an impediment to new architectures, whether it's spiking neural networks, state space models, so on and so forth? Because many of these models are not well suited for the chips that are being rolled out.
Durga?
Maybe I'll start with your question on that one. By the way, before convolutional networks became popular, spiking neurons were all the rage. Post SVMs and before some of the CV models that came in, I don't believe that is going to be as much of a challenge as we think it is. I think we've learned a lot of lessons since then. If you think about it today, whether it's in devices or in servers or in enterprise servers or all the way into data centers, increasingly most of the workloads, inference, has already gone into mixture of experts, which didn't exist, at least not to the level that it existed today, maybe 5 years back. But it's the same hardware that's been designed and provisioned a little ahead of time in terms of making sure that it works. I think the flexibility in terms of the way that we design our silicon and the software that actually runs on top of it is such that it's reasonably resilient for it. Now, of course, I'm not claiming that everything can be taken care of it. There's so many new models that are coming in, attention-free models, state-space models have been around in terms of what the promise is going to be. I don't think that those models are still going to be challenging the existing hardware to a point where someone says, okay, I just invested 50 billion and now I have to basically throw out all those racks and bring in new ones. I don't think we are at that stage at this point.
Thanks so much, Durga. I know we're coming up on time, so I just want to, first of all, thank our panelists. I think we've got some great perspectives here. We've talked, we're talking about
I can quickly respond to the data centers in space. I know, Roy, we were talking about energy portfolio and in one of the questions, and solar was one of the question of where does solar come into the energy mix, and there is no better way to harness solar other than data centers in space. You can move atoms around in space. That's going to be a challenge, but you can move liquid around, and you spend the right. And there's going to be some operational challenges, etc. But if you are trying to solve for energy, there's no better way to do that. So it's only a matter of time that we'll find out that it's more possible than we think.
And I want to add, I think from my perspective, there is a huge amount of research needs to happen even to think about if we are going to have a data center in space or we are going to have some other data sort of a generation sources. That's what I was talking about, having a really collaboration between the community to think about how do we do R&D in a not only in a government, but also in a partnership with government, academia, and industry to move the needle forward. Because it's not going to be a single organization, single nation. We need to learn collectively to think about maybe there is going to be a robotic system who are going to build those data center in space, and those we can control the robotic system from planet earth, maybe. But again, the research, fundamental research needs to happen in order to say the facts. Thank you.
Thank you so much. I think we're all out of time. Thank you so much to our panelists, and thank you to the audience.